Okay, let's talk about the first test over flat asphalt. So I had access to a flat asphalt test range and it was surrounded by woods. And it did the experiment, it made the measurements, and here are the results for vertical polarization. Now, we have to choose a sample frequency within the spectral recording at each range. So let's sample in the middle of the transmitter pulse. So this is the live graph I mentioned. The yellow curve is predicted power. The red is instantaneous measured power. The green is average measured power, and the cyan is the envelope of the highest and lowest powers at each range, with the absolute highest and absolute lowest measurements dropped. Now there's very little noise. Notice that there's very little noise at close range, but the noise, range noise, becomes larger at long range. Never mind the temporal range, and temporal noise, but it also gets larger. Now the noise appears to be caused by leaves on the trees. And at long range, the side scatter from the trees becomes comparable to the direct signal path length and the signal reflection from the road surface. Now the evidence for this is that I went back and did tests in the winter where there are no leaves. And on that day there was no wind either. So there is only side scatter from the tree trunks and the branches, which are basically big poles of ice at that time. And you can see in these measurements, almost all of the noise is gone. And there are several data sets I have that show this. Anyway, the bottom line is that there's something fundamentally right about the propagation model. In the absence of corrupting side scatter, the predicted and measured power levels agree to within a fraction of a dB. Now, the best way to check this would be by repeating the experiments at, for example, a decommissioned airport runway, but I never got that far, and I'm not sure such a thing even exists.